So now we're going to get into a discussion of molar mass. I talked about earlier the molar mass of elements, which, as I said before, is the same as the atomic mass numerically speaking, but the difference is, of course, their units. So in the case of molar mass, the definition of molar mass is given right here. It can be determined by simply adding up the molar masses of all of the atoms in the formula for the compound. So it's a very simple process. In fact, it's basically numerically the same thing as the formula mass for a compound, excepting that instead of AMU units, we use grams per mole for the units of molar mass. So it's very easy to calculate the molar mass of a compound such as this. All you have to do is consult the periodic table and look up the molar masses of the respective elements. So in the case of, let me write this here. So the molar mass would be equal to 2 times the molar mass of carbon, which is 12.01 grams per mole, plus 6 times the molar mass of oxygen, which is 1.008 grams per mole, let me continue down here, plus the molar mass of oxygen, which is 16.00 grams per mole. And let me do that on my calculator here. So 12.01 times 2 plus 6 times 1.008 plus 16.00, and the answer I got on my calculator is 46.07 grams per mole. All right, so that's essentially it. Nothing too complicated here. So that's how you get the molar mass of any compound. Just simply add them up according to the formula. Add up all the molar masses of the respective elements according to the formula. And I won't go through this one. It's the same process. In the case of ammonium phosphate. All right. Okay, so let's remind ourselves of something we talked about, the relationship between the mole, Avogadro's number, and the molar mass. Remember, the molar mass is the mass in grams present in 1 mole of a substance, and the same is true in terms of the Avogadro's number. It represents the number of particles in 1 mole of a substance. All right. So this is true not only for elements such as calcium, as you can see here, but it's also true for compounds such as H2O. All right. So 1 mole of water would have a mass of 18.02 grams, which of course you can get from adding up the molar masses of hydrogen and oxygen according to the formula. And that mass of water, which is equal to 1 mole, contains 6.02 times 10 to the 23 molecules of water. All right. And we can see the relationships that occur when you have a reaction between elements to form a compound. So here we have hydrogen combining with chlorine to form hydrogen chloride. And basically one can see that for every 1 atom of hydrogen, 1 atom of chlorine is required to produce 1 atom of hydrogen chloride. So if you expand that to Avogadro's number of atoms, you see the numbers here, atoms and molecules for hydrogen, chlorine, and hydrogen chloride respectively. And then that, of course, would be related to the mole, because Avogadro's number represents the number of atoms in 1 mole. So we can see clearly a mole relationship between the different substances, between the hydrogen, chlorine, and hydrogen chloride. And then down here we see the molar masses of the different substances, and therefore 1 molar mass of hydrogen atoms plus 1 molar mass of chlorine atoms will give you 1 molar mass of hydrogen chloride molecules. All right, so this kind of illustrates the relationship that exists between the number of atoms, the mole, the molar mass for these different substances as they combine to form hydrogen chloride. Okay, now I think I mentioned this before, but it's worth mentioning this again. When dealing with diatomic elements, make sure that you recognize them as such. In other words, in their formulas, you're going to have the subscript 2 here in the case of hydrogen, oxygen, nitrogen, and the halogens. All right? So it's very important that you understand the distinction between 1 mole of atoms and 1 mole of molecules. In the case of hydrogen, for example, 1 mole of hydrogen molecules will be 1 mole of H2. And you have to take that into account, especially when you're asked to, or when you need to determine the molar mass. Okay, so you could be given a question like this. Calculate the molar mass of 1 mole of hydrogen. Well, that is directly from the periodic table. The answer there will be 1.008 grams per mole. All right? But in the case of hydrogen molecules, it would be 2 times 1.008 grams per mole, which would be equal to 2.016 grams per mole. All right? So this is just a simple example underscoring the difference between 1 mole of hydrogen atoms and 1 mole of hydrogen molecules. Okay, so let's look at some problems here based on what we have just covered. So this question is asking how many moles of benzene, and it gives you the formula, are present in 39.0 grams of benzene. So as I said before, when doing problems of this type, I like to write down what is given, which is the 390.0 grams of C6H6, and you're to find the equivalent moles of C6H6. So in order for us to do this calculation, we need a molar mass of benzene. So I'm going to do a little calculation here. We know how to do that, of course, by adding up the molar masses of the different elements present in the formula. And when I did that, the answer I get is 78. So let me write here molar mass of C6H6 is equal to 78.11 grams per mole. So the way I would set up this problem is I would start with the 390.0 grams of benzene, and I would multiply that by 1 mole of benzene above. Oh shoot, sorry about that. 1 mole of benzene above and 78.11 grams of benzene below. So let me do my calculator thing. Divided by 78.11. And according to my calculation, when rounded to 4 sig figs, the answer becomes 4.993 moles. All right, so that's how we do that. Okay, so that's a relatively simple example. Okay, in this case, it's the reverse, basically. Different compound, ammonium phosphate, but the reverse is what is asked for. In other words, you're given the moles of ammonium phosphate. So let me write this down here. You're given 2.52 moles of NH4 3PO4. And you're to find the grams of NH4 3PO4. All right. So of course we'd start off with what we're given. Start off with a 2.52 moles of NH4 3PO4. And then we have to multiply by the molar mass in the form of 1 mole of NH4 3PO4 down here, and up here the mass in grams. So to do my calculator thing here. NH. Okay, so again, you'd get the molar mass by adding up the molar masses of all the elements present in the formula for the compound. And when I did that, I got 149.09, so that would go up here. 149.09 grams of NH4 3PO4. Alright, and that's it. All we have to do is use my calculator now to crunch these numbers. 2.52 times 149.09, and the answer I get here is 376 when rounded off to 3 sig figs, so this would be 376 grams of NH4 3PO4, and that's how you do that. Alright, so those are two relatively simple examples of solving problems where you go from grams to moles or moles to grams. Okay, now here's another one. Now this one is not as straightforward because this one is asking how many grams, gives you the mass in grams of nitrogen and is asking for how many molecules of nitrogen. So the way I would go about this is that I would start with the grams of N2. 1 minute. This thing is not cooperating. The grams of N2, I would convert that to moles of N2. And to do that, we're going to need the molar mass. And then I'll convert from moles of N2 to molecules of N2. And to do that, I'm going to need Avogadro's number. Alright, so down here, I'm going to start off with what we're given. We're given 56.04 grams of N2. And I would multiply this by a conversion factor, which represents the molar mass. So I'm going to have 1 mole of N2 above, and the molar mass of N2 below, which would be 28.02 grams of N2. That's 2 times 14.01. 14.01 is the molar mass of nitrogen. So the grams of N2 will cancel out here. And then the next conversion factor is where I convert from moles of nitrogen to molecules of nitrogen. And this is where Avogadro's number comes into play. So you're going to have 6.02 times 10 to the 23 N2 molecules. Alright. And that's it. All I have to do is use my calculator to work this out. So 56.04 divided by 28.02 times 6.02 times 10 to the 23. And according to my calculation, this works out to be equal to 1.2 times 10 to the 24 molecules of N2. And that's how you do that. All right, so in this particular example, I had to go through 2 conversion factors to go from grams of nitrogen to moles of nitrogen. So this is the conversion factor for that process. And then to go from moles of nitrogen to molecules of nitrogen, I have to use the conversion factor, which represents Avogadro's number. Okay, so that's another example. So here's another one. How many grams of nitrogen contains how many nitrogen atoms? Now to solve this, we could start off from the result of the previous question, because remember the previous question asks us to calculate the grams of nitrogen molecules, and based on what we determined from the previous question, we determined that the mass of nitrogen molecules would be or the moles, the number of nitrogen atoms, or molecules I should say, would be 1.2. What was it? Let me go back to the previous slide. It was 1.2, and actually it should be 1.2. Let me see here. It should be 1.20. I'm sorry about this, but this should be expressed in 3 sig figs. So let me put a 0 here. Okay, so that's the result we're going to use in the next solution. So it's going to be, go back to here. Let me cross this out. 1.20 times 10 to the 24 molecules of nitrogen. And because we know that for every molecule of nitrogen there are 2 nitrogen atoms, we can represent that in the form of a conversion factor here. So here we're going to have 2 nitrogen atoms and 1 nitrogen N2 molecule. And basically that's it. And when we work this out, you're going to get the answer being 2.40 times 10 to the 24 nitrogen atoms. And that's how we do that. All right. Okay. We're going to stop here, and the next topic we'll be dealing with is percent composition. Until next time.